Hello! The purpose of this video is to serve as an introduction to CFD, Computational Fluid Dynamics. And we're going to start with a very simple problem. Specifically, we're going to model one-dimensional heat conduction through a solid, a plane wall. And for this, we're going to use the ANSYS Multiphysics Suite, particularly ANSYS CFX, which is one of the commercial CFD codes that's available. We're going to start, first of all, by creating the geometry. So I've opened ANSYS Workbench, and I can do that very quickly here under the Analysis Systems. I can choose Fluid Flow CFX, left-click, and drag that over to the project schematic, and I can let go of the mouse button, and it will place a CFX instance in the project schematic. There we go. Okay, and I can start now by double-clicking on Geometry to create my geometry. Okay, I'm now in Design Modeler, which is the geometry tool for ANSYS. The first thing it asked me to do is to select my units, and I chose centimeters. If you chose something else and want to alter that, you can do so quickly under Tools, Options, Units, and then you can override the length unit accordingly. I want to create my 1D wall. I'm going to draw a rectangle in the XY plane and then extrude that out in the Z direction to create the wall thickness. So on my tree outline, I can click on XY plane, and I can right-click and choose Look At, and that will orient the plane toward me. I can switch from modeling to sketching now. And to help with my geometry, I can click on Settings, and on Grid I can say Show in 2D and Snap to Grid as well. Now I'm zoomed out, so I can use my scroll wheel. I can click in the window and then rotate my wheel to zoom in. I can now, on my toolbox, choose Draw, and you see I have a lot of basic shapes with which to work. I'll just choose the rectangle option. And my cursor is turned into a pin. I'll move that over the origin now and click once, and I'll just move this out and click one more time to complete this, and I've created a square. Using the Dimensions button, just general dimensions will work fine. I can just quickly put a horizontal and vertical dimension on that square, and since this we're looking at a 1D plane wall in the X and Y direction, mathematically it goes on an infinite amount. There is no temperature change in those directions, so it really doesn't matter how much material I have. I don't need much. I will use symmetry boundary conditions. So I'll just make it 1/10 of a centimeter in the X and the Y directions. Okay, now that I have that, I can extrude it. So I will click on the Extrude button. Note that that imports a extrude feature into my tree outline. And for my geometry, I will just click Sketch 2 and choose Apply. I will be adding material. I will go in the normal or Z direction. And for my length, I will choose 2 centimeters. Now that I've input all of those, you can see it has a lightning bolt there instead of a check mark, meaning I still have to generate that feature. So I'll click the Generate button. I now have a green check mark, and I can click and use the scroll wheel button to rotate, and I can see that indeed I do have now my wall of 2 centimeter thickness in the Z direction. Before I move on, this is also a good part or a good instance to create named selections. That will help me later on when I create my boundary conditions. So my X and Y directions are symmetry. I can move up to the top here, choose a face selection, and I can hold down the Control button as I left click, and I can choose all 4 faces. Now with that, I can right click and create a named selection. All 4 of those faces are chosen. For the name, I could call it maybe symmetry. 4 faces, I can click generate. I've now created that. My first boundary condition will be at z is equal to 0. So I'll click that, right click, name selection. I'll just call this boundary condition 1, BC1, and I'll generate it. Now I'll rotate out and I'll choose my second boundary condition, right click, name selection, call it BC2, and generate. Okay, so I have my extruded wall, and I have labeled symmetry boundary faces, boundary condition 1 face, and boundary condition 2. Well, you can choose the Save button, or you can just close out of Design Modeler and it will automatically update. And you see now the geometry cell has a check mark. We have a valid geometry that's been created. At this point, it'd probably go ahead and be a good idea to save this, which will save your entire workbench project. You can choose a location and go ahead and give it a name. And now we can move on to the next location, which is creating a mesh of that geometry. So double-clicking should open the mesh feature. Meshing this geometry will be pretty simple. Since I'm dealing with 1D conduction in the z direction, nothing is happening in the x direction or the y direction. There is no heat conduction, there is no temperature change or gradient in those directions. So I do not need any mesh in those directions. What I want to do is divide this block, this plane wall, into sections in the z direction. To do that, I can click on Mesh under my outline. I will right click and insert a method. So it wants to know what geometry. I will click on the entire geometry, click and choose Apply. So it's now identifying the one body, and now it's wanting to know the method. I will click on that cell and there's a drop down list, and I'm going to use Sweep. What Sweep will do is it will take whatever mesh is on the first face and then just copy that as it meshes throughout the z direction. I will change automatic to manual source and target, and now it wants to know what the source is, or the face that it's going to copy. So I click there to turn it from yellow to the Apply button, and now I'll click and drag my scroll wheel on my mouse to rotate to my z equals 0 face. I will click to highlight that, and I will click Apply. And now I will rotate back. Note you can always click the triad to switch into isometric view as well. And here's my z equals 2 centimeters face, and I will click and choose Apply. The type is number of divisions, and the sweep number of divisions is default. I can click that, and now we can determine how many cells we want to divide this domain into. So maybe I'll just pick 4 to start. Okay, everything has been input, so I can click the Update button. The mesher will activate and show progress. It's not showing it because the faces or the sweep is highlighted. I can click on Mesh to show the mesh. And now you can see that indeed I have 1 cell, 2, 3, and 4. I've now divided my domain into a mesh with 4 nodes or control volumes. So at this point, I'm done with the meshing application. Again, you can go to File and Save, or we can just X out. And we're back to Workbench. So now we see the green check mark for geometry. We have a valid geometry. We have created a valid mesh from that geometry. Now we can set up the physics of the problem using ANSYS CFX. So I will double click cell 4 to open ANSYS CFX. I am now in ANSYS CFX. Actually, CFX Pre is the specific program. And you can see that the workbench has automatically imported my geometry and the mesh. If I click on the CFX mesh file, you can see it divided into my 4 control volumes with 4 nodes in which I'm going to solve for temperature. To do that, I need to work my way down through the outline, filling in information where I need it. So under Flow Analysis 1, I can double-click on Analysis Type. No external solver coupling, and this is a steady-state solution. I can click on Default Domain, which is my object. It's already captured. Now, this represents a solid, not a fluid, so I will change from a fluid to a solid domain, and it will automatically pick aluminum for the material. I'll just use that right now as the default. I can change the parameters a little bit later here. I'll move over to the Solid Models tab. I am solving thermal energy heat transfer with no radiation. That's fine. And initialization will just automatically choose a first guess to start the solution process. So I'll click OK to apply those settings. Now I need to bring in my boundary conditions. I do that underneath here. I can right-click on Default Domain, Insert, and I can insert a boundary. Now the nice thing here is that if I type in the named selections, it will automatically associate with those. So I could type in symmetry, which was the name I chose for the side faces, and it already grabbed that location. The symmetry boundary type, there are no other settings for it. I can choose OK. And you see that it's applied those on those faces. I can now right-click and insert another boundary, BC1. It automatically grabbed location BC1, which was my wall at z equals 0. And that boundary type, I have 2 options, a wall or symmetry. I will choose a wall. And then under boundary details, I have several options. Adiabatic, I could set the temperature, I could set the heat flux, I could set a heat transfer coefficient. I will set the temperature. For me, it is 373 Kelvin, or I could also have input that in Celsius. And I will click OK to apply that. I need to apply for one more domain. As soon as I do that, this leftover default will disappear, meaning I've successfully applied all of my boundary conditions. That is BC2. Click OK. That is also a wall, so I will click over to boundary details. Now on this boundary, I have a heat transfer coefficient. And for that, I need 2 more pieces of information, the first being the heat transfer coefficient. The problem I specified for my class, we have 20 watts per meter squared Kelvin, and the outside fluid temperature was 25 Celsius. I can click OK to apply that. Now one further thing, the problem I've given to my class has heat generation inside this wall. So to include that, I want to right-click and insert a subdomain. We can call it whatever we want. I'll use the default name. The location, I only have one geometry, so there's nothing else to choose. I could have also selected it from this drop-down, and it highlights. And then I can move to the Sources tab, activate it, an energy source, and then I can click on the energy button. I can specify the source, and it's automatically looking for watts per meter cubed, so watts per volume. And the problem specified 500,000, I believe. We can apply that. I've already taken care of the initialization. We don't have to worry about interfaces. Solution units, the default is OK. We can now move to the solution control. I'll use most of the default options. For the maximum number of iterations, I just might move that up to 400. Fluid timescale control we don't have to worry about. Solid timescale control, we'll leave that on automatic as well. The residual target, I'll move that down. Right now it's 1 times 10 to the negative fourth, and I'll move that to 1e negative 8. And for heat transfer, it's always good to set a conservation target. The default is 1%. And that means the computer program is not going to stop iterating on a solution until the first law of thermodynamics is satisfied for this domain. In other words, energy generated minus the energy that's going out through the boundaries must balance within 1%. I'll click OK. Next up is the output control. And the best use here is under the Monitor tab, and I can activate that. The solution will be showing us residuals as it iterates towards a solution, but it's always good practice to go ahead and monitor a quantity of interest to see how well it's converging towards a solution. We're solving for temperature, and in the homework problem I gave, we were looking specifically for the maximum temperature in the wall. So why don't we create a monitor point that looks for that. I'll call it Tmax. And under my options, I'm going to use an expression. Now I learned this through using the CFD post and the documentation that comes with the program. But what I will look for is finding the max val, so maximum value of the variable T, temperature, inside the default domain. Max val of temperature inside the default domain. And I will click OK to apply that. Oops, it did not recognize default domain. This is the message box, and it helps out a little bit. I need a space there in between those two to match what CFX pre was using. That goes away, and you see I'm matching now the name, default space domain. One more thing. The problem I gave specified a thermal conductivity of 5 watts per meter Kelvin. We said this was aluminum, so I'm going to come down to the Materials tab. I will double click on aluminum, and I will move to Material Properties. I will keep everything default. It's not going to be it's not going to have an effect on our solution except for transport properties. I will expand that, and thermal conductivity, instead of the default for aluminum of 237, I would change that to 5 watts per meter Kelvin. Okay, so I have fully set up my domain and the boundary conditions as well as the solution parameters using CFX pre. I can close out to return back to the workbench. At this point, it's always a good idea to go ahead and save. We now have a defined geometry. We've broken that geometry into a mesh with several nodes at which we wish to solve for temperature. We've set up the domain and the boundary conditions. All these things now result in a set of simultaneous algebraic equations that have to be solved. Somehow the matrix has to be inverted to solve for the unknown temperatures. And that's the purpose of the solution cell. We will double click on cell 5, which should open the solution program. Okay, the solver manager is up, and it's asking me to define the run. A lot of the things can be left as default. The input file is taken care of by Workbench. I'll use the current solution data if possible. Since we have not tried to solve this before, it will use the initial values that CFX pre automatically defines based on our boundary conditions. The computer and the license, everything we'll leave as defaults, and we will click Start Run. So at this point, all of the buttons we chose in CFX Pre are going to be turned into a text file that is input to the Solver Manager program. There they are. This contains the shorthand code you can see for all of the boundary conditions and options we've chosen. The solution process has started and it's already finished. Fluid flow has completed normally. Results are in. It tells you the location of the data file. If I look at the plot here, notice that I'm solving for heat transfer, in other words, the thermal energy equation that I've used to solve for heat diffusion. And it's dropped below 1 times 10 to the negative 6 for my residual. I can right-click, go to Monitor Properties. Under Range, I can change that lower bound to 1 times 10 to the negative 8. Okay, and now we get a more complete picture of what has occurred. The matrix equations are being solved iteratively, and what you're seeing is a residual error estimate based on that. We don't know the error exactly. This is a estimation of the error on the matrix solution. What we can tell is that the error has dropped almost 1, 2, 3, 4, 5, 6 orders of magnitude. That's a very good solution. And it has essentially bottomed out. We could not quite get to 1 times 10 to the negative 8. We've gotten to the limits of the machine, probably in terms of the number of nodes, the domain step size, and the single point precision of the solver. I can click on user points, and now this is the monitor of what I set up for Tmax, the maximum temperature inside the domain. So if we had stopped at 1 times 10 to the negative 4, the default, that was about 60 iterations in the solution process. At 60 iterations, you see, I would have been off by about a degree on my solution of interest, the maximum temperature. So it always helps to try to plot how what you were looking for changes throughout the solution process. And we see that I pretty much hit a final value for the maximum temperature at about 150 iteration. It says time steps. You can interpret those as essentially iterations in the solution process. And going back, that is about 1 times 10 to the negative 6. So after the fact, we can go back and see how well we were able to achieve a solution. I can scroll up through this text file. It tells us a lot of information. It took 8.6 seconds to go 400 iterations in the solution. I can scroll up a little further. Okay, note the thermal energy equation. Remember I said we were driving this to below a 1% balance on the first law of thermodynamics, and it tells you how much thermal energy was going through boundary condition 1, boundary condition 2, and how much was generated in the subdomain. And the resulting imbalance, when you add all those together, is 0.0014%. So we have good confidence, at least that the first law of thermodynamics has been met. Now we can see each of the iterations. The rate, I'll scroll to the top here. Rate is giving us an idea of how much the solution is changing from one iteration to the next. And then we have our root mean square of the residuals for each of the nodes and the maximum residual possible. This is showing us the root mean square residual. So it's giving us a graphical interpretation of this number. And then this column is giving us information about the solution of the matrices. If I scroll up further, it tells us information about the mesh, mesh statistics, orthogonality, angles, expansion factors, aspect ratios. We can see that it's saying everything we chose was in the very good, big letter OK range. It tells us we used 4 elements. And if I scroll through again, this is giving us a summary of all the information we chose graphically in CFX Pre. So I have my solution. I can close out of the Solver Manager. I see the check mark. And now finally I can open the results CFD post to get the data and process it in ways that I would like. So I'm finally in the CFD post-processing application, and it's loaded my geometry as well as the solution. I can now view, visualize, and draw data out of that solution in many different ways. Let's first try to visualize the mesh, for instance. I can click on the symmetry, for instance, in the default domain. And a good way to view the mesh would be to double-click. Under Render, I can scroll down and I can click Show Mesh Lines, for instance, and apply. And so that gives us a good visualization, a reminder that we created 4 elements or control volumes in this case. Now if I like this, this view that I've created, I can save it into a report. To do that, I can right-click and choose Copy to New Figure. I can name it whatever I want. And note that that has now moved what I've created here. It's copied it and made a figure there. Another thing I can do is maybe visualize how the temperature changes through the domain. I could do that, for instance, with a contour plot. So I could turn off the mesh visualization. Under User Locations and Plots, I could right-click and insert a contour. I could name it if I wanted to. I'll just use the default. And now that opens this details. My domain, I can use everything. The location, I want to visualize the temperature as it changes along what I'm calling the symmetry. My variable is temperature. I can choose Apply. Okay, and I'm visualizing I have the coldest temperature at my starting point, z equals 0, and the temperature increases as I move through the domain, and then it's hard to tell what's going on here due to just the gradient. This is one of the shortcomings, I guess, of a contour map. I am always a stickler for making graphs as readable as possible, and dealing with Kelvin and with this scientific notation, that's not very readable. We can change that. I'll show you first how to switch to Kelvin. I can go to Variable tab, I can double click on temperature, and I can change that variable from displaying Kelvin units to Celsius. That's helped a little bit. I'd really like to get rid of those scientific notations there. To do that, I can click on the default legend view. I can move the legend around as I want, but I'm going to go to Appearance, and instead of scientific, I will change it to fixed, precision 3, click Apply, and now we have, I might even take one more digit off. Okay, now we have a much more readable legend here. We have our boundary condition hopefully being met here at around 100 degrees Celsius, and then temperature increases, and something else is going on here. Increase or decrease, I can't tell exactly. If I like this, I could right-click and copy to new figure, figure 2, and we see that's brought into our report as well. It might be helpful to actually create a 2D plot of temperature versus z distance. To do that, I'm going to, under User Locations and Plots, right-click, Insert. I will insert a location, and I'm going to choose a line. I'll just call it maybe center line. Choose OK. So there's my center line, and I will define the line by 2 points. Now 0, 0, 0 is the bottom corner of my domain. I'm going to pick the halfway point, which should be, there we go, half of a millimeter. based on the geometry I set. And to find that, you can slide this, which you put it halfway. That should be halfway across the domain in the y-axis now, 0.005, and then the z dimension is 0. My second point is going to be the same x position, the same y position, and it's going to be at the end of the domain, which is 2 centimeters, 0.02. And again, I can remember that through the slider. On the line type, I'll just sample 100 times along that line, and I will click Apply. You can't see it because the contour is turned on. I can turn off the contour by checking on it. And now you can see a yellow line proceeding through the domain that I've created. Now I can plot temperature along that line. To do that on my report, I will right-click and insert a chart. I can name it whatever I want. I'll just use Chart 1. That opens the chart and then my detail pane. I can give it a title, so temperature distribution in a plain wall. You could add a caption if you would like. I will move to data series, and under location I will choose my center line. Okay, and it's automatically plotting temperature on the y-axis versus chart count, and I'm not sure what that is. So I'm going to go to my x-axis, and under my variable, instead I want the z direction. There we go. My y-axis looks good. It shows temperature. Everything else I believe I'm happy with. So I now have a plot that is showing how temperature is varying through my domain. And I see that in reality maximum temperature occurs here, and then the temperature decreases slightly as I approach my convection boundary. I see my boundary condition is met here, 100 degrees at z equals 0. And I see how coarse this is because I only chose 4 nodes. So if I choose more nodes, reducing the distance between each node, I would expect my error to decrease and my approximate solution to increase in accuracy. If I wanted to view my entire report, I could click on Report Viewer at this point. And it gives a nice report, shows the graphs that I created. I could publish this to a HTML file if I wanted as well. Oh, one more thing. Expressions. What is the maximum temperature? Well, I could try and visualize it in this graph, approximate it, or I could get it through the Calculators tab. I could use the function calculator. And this has a lot of nice functions you might use to find forces, for instance, when we're doing fluid flows, pressures, integrals, anything. What I would like is to find the maximum value in the entire domain that I was using. And for the variable, I'm looking for temperature. I can click to show the equivalent expression. And this is how I learned to use this in CFX Pre to create monitor points. You learn the code this way. And anyway, it's telling me that my maximum value is 387.6 Kelvin, which would translate to this 114.5 about, or 0.6 Celsius that I can see on the graph. Okay, so I've used CFD Post in order to visualize my meshing. I have visualized the solution, in this case the temperature in a contour map. I've plotted it on a chart, temperature versus distance, and I've used the function calculator to determine what the maximum temperature is. All in all, a pretty good day.